All right, welcome back, everyone. We're gonna move on to section 14.6, directional, derivative, and the gradient vector. Suppose you stand on a surface fxy, and if you walk in any direction, what is the slope of the function in that direction? If you look up this question, right, this one thing that the direction, direction here is governed by a vector. We're gonna focus on the unit vector. Right? The reason why we use the unit vector u is because it just makes it easier to do the computation. The magnitude of u is 1. So that is the reason why we want the direction to be parallel to a unit vector u. So let's draw this thing now and see how we can do it. Okay, so if I draw the surface, it's gonna be pretty messy, right? So I pick a point right here and another point right here. These 2 points, one of them is gonna be project them down here, right? So let's say x naught, y naught. And then the other one is going to be so you see that they are not the same. X, Y, yeah, just X, Y here. X, Y. So when you do the projection, right, at the beginning of the projection, you're going to have this, and at the end, you're going to have this one. We can actually draw a vector here. So let's say that we pick the point so that we get a unit vector, u equal AB. And this unit vector is going to go right here, x minus x naught here. We can set it equal to some multiple of A, and then y minus y naught, we can set it equal to some multiple of B. This is the HU, HA, HB. Okay. Next thing is that, well, we want to get the slope on the surface that is in the direction of the unit vector. The 2 points, they are on the surface. I think now I can draw some surface on here. Let's draw some surface on here. Fxy. You can connect them through a trace. So it's become a trace right here. So Tracy. Yep. This is the point x naught, y naught, z naught, because we want to find the slope of the surface at this point in the direction of the unit vector. So here come, I'm going to draw the tangent line here. Actually, let me redo the point. You know, you don't have to pick these 2 points here. I'm just going to pick the point so that it's a little tricky to pick the point, but I'm going to draw the slope of the tangent line. So it's parallel, and then I'm going to pick the point later. It's tangent line. I can pick a point right here. Slope of the tangent line. Yeah. Well, it is parallel to the unit vector. Next step is, how do we find the slope of the tangent line? The slope of the tangent line will tell us the slope of the function in the direction of the unit vector here, right? Let where the magnitude of u is equal 1, so make sure it's the unit vector. Right? Then HU is going to be HA, HB. Yeah. For some scalar, H, so that HA is equal x minus x naught. And HB equal y minus y naught. From here, you can solve for x there. HA plus x naught, HB plus y naught. Okay. So now notice that the slope of the tangent line at x naught, y naught in the direction of the unit vector u is limit. Well, the slope of tangent lines is going to be a limit of the slope of the secant line. So limit h go to 0, right? And then we know the slope of the secant line is just going to be a f x y minus f x naught y naught over h, right? Slope of tangent line at x naught y naught in direction of the unit vector u is way too long, so there's a better name, right? Mathematician, we call it the directional derivative of f at x naught y naught is equal to limit h go to 0. X naught, I mean x is ha plus x naught, or x naught plus ha is the same thing. Actually, it looked nice with x naught plus ha because it's a little distant from x naught. No, this one. F x naught plus ha y naught plus hb minus f x naught y naught over h. Okay. I'm gonna let gh, right? Because this is the limit h go to 0 here. So we can have a function gh to be fx0 plus ha y0 plus hb. Okay. So yeah. So what's that mean? G of 0 is going to be. So G of 0 is going to be f x0 y0. Ah. And if you look up this thing here, if you do this, that means this is going to become limit h go to 0. G h minus G of 0 over h. Oh my God, what is this one? This is the definition of derivative. This is exactly G prime of 0. Yeah, since look at this, look at what we have. X equal x0 plus ha. Y equal y0 plus hb. See, g h is the same as f xy. So we can do a g prime h equal, oh, we got to use the chain rule. Fx, taking the partial derivative with respect to h, gonna give us a. Taking the partial derivative with respect to y, gonna give us b. G prime of 0 is gonna be fx x0 y0 a plus fy x0 y0 b. And then what is the a and the b here? Let's see. A and b, they are the component of the unit vector. But this is what we have here. And this is exactly the directional derivative of the function at f x0 y0. If x0 y0 is an arbitrary point, if you have any question, let me know, guys. Make sure that you follow the direction here. Then directional derivative in the direction of the unit vector is d f x y. In the direction of the unit vector is going to be fx a plus fy b. Oh, look at this one here. Well, you can do this, right? You can cut it into two vectors, fx fy dot ab, and fxy, we call it, we have this notation here. It is the gradient vector and it is the unit vector. The directional derivative of a surface function is the dot product of the gradient and the unit vector. All right, here comes some example here. Show that fx is parallel to the x-axis. Using directional derivative. Okay, so we can do this one. So we just have to pick a unit vector, right? So unit vector in the direction of the x-axis. A trick to do this is that you're gonna have to do this in here, x, y, right? And then your unit vector, that is u here. So you can pick the unit vector to be 1, 0. It's the unit vector here in the direction of the x-axis. Next, we're gonna do the directional derivative of fxy in the direction of the unit vector. So that will be the dot product of the gradient vector multiplied to the unit vector, and it is fx fy multiply to this is the dot product. I just multiply unit vector is 1, 0. So just fx. How nice. Very short. If u is defined by an angle from the x-axis, then what is du fxy? U is the vector that is defined by the angle from the x-axis. So of course, u always have two components, the x and the y component. Right? The x component here is adjacent to the angle, so it's cosine. The y component is sine. Now, du fxy is it's the fx fy dot the unit vector. The unit vector here is the cosine theta. Let fxy equal x squared plus 2xy minus y to the 3. Find the directional derivative at f32 in the direction of the vector v equal 1, -1. Okay, so according to the definition, in order to do the directional derivative, you got to do two things. Huh? You got to do the gradient vector and the unit vector. Huh? It'll be phi gradient vector fx fy. Okay, so let's do it. Fx is going to be 2x plus 2y. Fy is going to be 2x minus 3y squared. Right? Now we have to evaluate at the point 3, 2 here. So the gradient vector at 3, 2 is going to be 2 times 3 plus 2 times 2, 2 times 3 minus 3 times 2 square. What do we have here for this one? 10 6 minus 12 is -6. Okay, so got that one. Find the unit vector. U. Well, we know the unit vector U is gonna be the vector V divided by the magnitude of the vector V. So it's gonna be 1 right? Divided by the square root of 1 square plus -1 square. Root 2, so it's going to be 1 over root 2, -1 over root 2. Okay, we got it, right? So in the end, now the directional derivative of the function at the point 3, 2 in the direction of the unit vector is the dot product of the gradient vector at the point 3, 2 and the unit vector. Yeah. So that's going to be 10 -6 dot 1 over root 2 -1 over root 2. Am I going fast, slow, or okay? Let me know. 10 over root 2 plus 6 over root 2. Right? It's going to be 16 over root 2. Let me do here. Directional derivative in the direction of the unit vector at the point -1, 2. Right? So here comes just the notation here. Where I have to give you the surface. Fxy is equal to x squared minus xy plus 3y squared, right? And u is cosine theta, sine theta. The gradient vector fx fy 2x, right? No. Minus y, fy is going to be a minus x plus y. Okay. gradient vector evaluate at -1, 2. So this would be 2 times -1 minus 2 -1 plus 6 times 2. Right, so what do we have? We have -2 minus 4 and 1 plus 12 is 13. Okay, yeah. Next one is going to be we already have the unit vector, but then we need the unit vector is not in terms of cosine theta, sine theta now. We got to figure out the angle theta here. So we know u is equal to cosine theta, sine theta. Need to find theta. Can anybody give me what is the angle theta here? So we can do cosine and sine. There's another trick that you can do. X equal -1, y is equal to 2. So this is the angle theta right here. Right. So what would be cosine of the angle theta? A squared plus b squared c squared. So -1 squared plus 2 squared equals c squared. It is 5 equals c squared. So c is equal to root of 5. Right? 1 over root 5. Sine is going to be opposite. So 2 over root 5. Okay, so we have u and we have the gradient vector. I should be able to do this problem now. Directional of f -1, 2 is the every time I have to do this thing here. The gradient vector at -1, 2 dot the unit vector -4, 13 dot -1 over root 5, 2 over root 5. And what do we have? We have a 4 over root 5 plus 26 over root 5, and that will give us 30 over root 5. Just right on time.